In this video, we're going to tackle something called optimization, which is probably going to be the most difficult thing we do this semester. It has to deal with extrema, and specifically absolute extrema, whenever we're trying to find the absolute max. Another word for absolute is global, or potentially we're trying to find the absolute minimum. If we're trying to make something as big as possible or as small as possible, there's a process called candidates test, which we can use, and that's what the first couple of examples are going to be over. And then we're going to get into some optimization word problems, and those are going to be a little bit tricky. But in general, we got to just know the candidates test first. What is an absolute extrema versus a relative or a local extrema? That's what this first chunk of text says. Again, you can pause, you can read it on your own, or you can pull up the PDF version of the notes. I'm not going to read it to you. But look at this little diagram at the bottom of the first page. It shows us the difference between relative. Relative means, hey, around that point. So if I check a little bit to the right, and if I check a little bit to the left, in the general vicinity around that point, is that y value the biggest y value? Or if it's a minimum around that point in the general vicinity, is that point the lowest y value? Right? So relative extrema, you have to check a little bit to the right, a little bit to the left, and if your point is either the high spot or the low spot in that little interval, you have a relative extrema, either a max or a min. But the absolute or your global, that means big picture for the function overall as a whole. What's the biggest y value the function ever gets? And then also the minimum is what's the lowest, right? So in this box it says there's some point that is less than or equal to every other point, and so that is your absolute minimum. And then your absolute max, of course, it's the y value that's bigger than every other y value. So the difference, relative, only in that little area. And absolute means for the whole entire function. Okay, let's go through and let's practice. Let's practice doing some candidates tests, which is how we can find the absolute max and the absolute min. First couple are going to be just pure math, and then we're going to get into some word problem ones, probably in the next video. Okay, so here's the process, and again, this is called candidates test. The candidates are all of the things that could potentially be the minimums or the maximum, the absolute extrema. Now, going back to this picture we had on the previous page, of course, like if your function would have just ended like this, then your absolute max could have been one of the relative maxes in the middle. Or if you have a restricted domain, right, it stops and it starts on both sides, then your absolute max could be one of your endpoints. Okay, your absolute min, it could be one of the relative mins. Right here, it looks like it's this left relative min. Or if the function would have just stopped, then it would have been the left endpoint. And then that would no longer have been any relative. That would have just been strictly an absolute. Okay, so your absolute extrema, it could be in one of the relative in the middle, right? If you're looking for the absolute max, it could be one of the relative maxes in the middle of your interval, or it could be the right side or the left side of your interval. And same thing. So your candidates, all the values of x that could potentially produce the biggest x or the biggest y or the biggest or the smallest y value. Your candidates are all of your critical points and your endpoints. So critical values and your endpoints, those are your candidates. Those are the things that might produce your absolute extrema. And then we just test them by making a little table. Okay, so let's practice. Here we're going to find the absolute extrema for this same function, but twice. We're going to do two different intervals. Okay, but the first thing we need to do is find the candidates. I know I have the endpoints. We'll do this one. We'll call this one A, and we'll call this one B. So I have two candidates already. You have the left side, -4, and then you have the right side, 2. I think that should be a comma. And then we have to go find the other candidates, which come from that first derivative being 0, or the first derivative being undefined. So the first step is going to be take the derivative. Okay, and then you would always check, is that derivative ever undefined? Most of the time, no. So here we're just going to set it equal to 0. You could factor out a 6. And then let's see, that looks like a +2 - 1. So x equals -2 and x equals 1. There are your critical points from the middle of this interval. Now we're going to need to take those critical points and we're going to need to test them and the two endpoints to figure out what type of absolute max we're going to have. Okay, so how we test them is we're going to make a little table. We're going to collect all those important candidates, all those x values that could be the max or the min. This is the work for A. And then we're going to plug them in to the original function. Because we're going to see which one of these values, you have the left side, you have the right side, and then it looks like both of those critical points are in the middle. That's good. If for some reason you had another one that was outside of your interval, you just wouldn't care about it, right? We're only investigating this function on this interval. So if you had any other critical points that are outside of your interval, you would just ignore them. Okay, but I take my two endpoints. Always, always, always test your endpoints and the critical points in the middle. And I'm going to test them by plugging into the original function because I want to see what are these y values. And then I'm going to pick the biggest and the smallest one. Okay, so pretend I have my calculator. I'm not going to actually get it out because I already know the answers. But pretend I'm just going to type this function, the original function, into my calculator. And then I would just evaluate it by plugging in -4. And you would get out -32. If I plugged in -2, you would get out 20. And then you would get out -7 and 4. Okay, so that's the values you would get if you were plugging in those candidates, your endpoints, and your critical values, if you were plugging them into the original function. And then here it's pretty easy. We can see which one of those four numbers is the biggest. It's clearly the 20. So there's your absolute maximum. It's going to be 20 when x equals -2. Remember, the max value is the y-coordinate, and then where it happens is the x. And then the minimum, the smallest of these four numbers, looks like the -32. Okay, so here we go. Let's write the answers. F has absolute max of 20 when x equals -2. I always kind of like to write it as a sentence stem, right? F has absolute max of blah, and you fill in the blank with the biggest number when x equals blah, and you fill in the corresponding x value. And absolute min of blah when x equals blah. So you just find the lowest value, which for us would be the left endpoint, the -32. And there you have it, right? So there's our answer for the part A. We found the absolute extrema for that function f, but only on this specific interval. Now let's go ahead and let's do kind of the same process, but instead of using the interval from -4 to 2, let's only use the interval from -1 to 2. So -1 and 2. Now you don't have to redo the derivative work because it's the same function, so it would be the same derivative, it would be the same critical points. But now I wouldn't really care about the -2 because it's not in your interval. So now the only critical point in the middle that you'd have to test is 1. Again, plugging those values into the original function. I know 1 is still going to be -7. I know 2 is still going to be 4. But now I have a new left endpoint. And so that one would be 13. And so if you're looking at a different piece of this graph, now a little smaller interval, now we're going to have potentially different maxes or different mins. It may still be the same because that point may still be in your interval, but here that one actually dropped off. So it looks like we're going to have two new answers. So let's write the answer. F has absolute max of blank when x equals blank, and absolute min of blank when x equals blank. Ooh, I made that equal sign too big. And then we just have to fill in the blank. Remember, here's the work for the part B. They weren't initially labeled A and B. I just did that for myself. So the maximum value, that would be the biggest y-coordinate, which now is going to be 13. And that's going to happen when x equals -1. And then the minimum value, so there you have it. That's your process of candidate test. That's how you find absolute or global extrema. You find the critical points, and then you have to take them and your endpoints. Those are all your candidates, right? The endpoints and your critical points. Those are all the x values that may produce out the absolute max or the absolute min. I collect all those critical points and I test them by making this table, and then I plug into the original. Do not plug these in to the derivative. If you plug -2 into the derivative, you're going to get 0. If you plug 1 into the derivative, you're going to get out 0. Setting the derivative equal to 0 is how you find the x values, but you test the x values by plugging them into the original, because we're trying to see what are the y-coordinates so that I can find the biggest and the smallest that the function ever hits. Okay, one more example, and then we'll probably stop for this video, and then we'll get into the word problems with the next one. Okay, find the absolute extrema on the interval. It's a typo. Extreme should be extrema on the interval 0 to infinity for this function 2x e to the negative 0.2x. Oh my gosh, that's so terrible. I'm going to change this to a fraction. So I have f of x equals 2x e. Let's see, 0.2 would be 1/5. So negative 1/5 x. So there's your function. I know I have a left endpoint, but since it's a parenthesis, you really wouldn't want to include it. And then here, there is no right endpoint. So if you want to, you could always kind of look at this graph. We'll look at that in just a minute. But let's go ahead, take the derivative. Let's find the critical points. And let's see what else we could test. Going to need product rule for this derivative. You have this first chunk, which is 2x. Then you have the second, which is the exponential. So you need the derivative of the first times the second plus the derivative of the second times the first. Still need to do the derivative of the second. And I know the derivative of e to the stuff is e to the same stuff. And then chain rule says you're going to kick out the derivative of that inside piece. So there was your derivative. Product rule, derivative of the first times the second plus the derivative of the second times the first. Let's simplify it. I think you can factor out the exponential from both terms and a 2 from both terms. So I think you could factor out, let's see, a 2 e to the negative 1/5 x. And then you're going to be left over with just 1 minus plus negative, so that's minus, and then you have x over 5. Okay, now this is never going to be undefined, so we're just going to set it equal to 0, try to find the critical points. So we'll try to see, does that ever equal 0? Or does this ever equal 0? Well, no, the exponential function, even though it's an exponential decay, it's never going to be 0. So that one has no solutions, no critical points coming from that specific factor. But we do have one here. I think if you plug in 5, you'll get 0. So we have just the one critical point. Let's plug it in. Right? If I plug it into the original function, we'd have 2 times 5 e to the negative 1/5 times 5. So that's 10. E to the negative 1. This would be 10 over e. So there's your y-coordinate. Now there's no other real candidates. Your left side would be 0, but since it's got a parenthesis instead of a bracket, you really wouldn't care, right? It's going to be an empty dot if you were to graph it, and you can't have an absolute extrema when there's an empty dot, right? You can get really, really, really close to that point, but you can never technically get to that point. So let's kind of look at this graph, and let's see. I'm not going to put it on my calculator. Just pretend I am. I already know what the graph is going to look like. It's going to go at the origin. That's where the point is supposed to be. If you were to plug in 0, 2 times 0, it's going to be 0. It's just we want it to be an empty dot because of its non-inclusiveness. And then the function ends up looking something like this, where it goes up, and then it's going to actually come back down. So it does end up having a maximum, and the y value of that max is 10 over e. Remember, e is a number. It's about 2.7. So 10 divided by about 2.7, it's going to be probably between a little bit less than 5. Okay, so there we have it. We couldn't really do any other candidates test because there were no other candidates. You can't plug in infinity. It's going to be a 0. But the graph never quite gets down to 0. You can't really plug in the 0 because it's undefined. Because of the parentheses, it's an empty dot. So you could, if you wanted to, make the little table. You could see, hey, if I were to plug in both of those sides, I would get out 0. So you can see on the left side, it's going to be at the origin. On the right side, it's going to get close to the x-axis. And then I know, hey, at that critical point, I ended up getting 10 over e, which is like about 3.68. So even though that's an empty dot, because of the parentheses, and because I know that's your horizontal asymptote, you're never going to quite get to those, so you won't have any absolute minimum, but you can conclude that that is definitely the biggest. So we'll see f has absolute max of 10 over e when x equals 5. F has no absolute min. Because of the empty dot on the left, where the min really would be. And because of the arrow on the right, it's never going to quite get to the x-axis, it's just going to get closer. You're not going to end up having any absolute minimum. You do have the max, but you do not have any minimums. It's kind of rare when that happens, but it could. Okay, so we're going to pause there for this video. When we pick back up in the next one, we're going to start to apply this optimization, finding the absolute max or finding the absolute min. We're going to apply those to some word problems, and these are going to be a little bit tricky. It's probably going to take 2 more videos, unless I want to make one really long one. But kind of brace yourself for the next video, because it's not going to be super easy.